Hey there, physics folks. Let's take a look at one more UCM FRQ for AP Physics 1. If you are wondering or you want some reference, this particular question appeared on the 2001 AP Physics B test. It was question number 1, so if you want to look this up through the College Board. So first of all, we have a vertical circle. It says a ball of mass m is attached to a spring of length r and is of negligible mass, meaning the mass of the string does not matter. The ball moves clockwise in a vertical circle as shown above. When the ball is at point P, the string is horizontal, so that's when it's over here. At point Q is at the bottom of the circle, and point Z is at the top of the circle. So they don't mention this, but if it were at point Z or point Q, the string would be vertical as well. Air resistance is negligible, and this last statement is really important because it's also somewhat similar to how the AP Physics 1 test, the test that you'll all take in the spring, there are very few numerical measurements on the AP Physics 1 test for the FRQs. So it says, as it frequently does, express all algebraic answers in terms of the given quantities and fundamental constants. What kind of fundamental constants? The acceleration due to gravity, universal gravitational constant. I know that doesn't apply here, but those are these fundamental constants that we know of. Okay, so we have a vertical circle. So again, I always like you guys to sort of think about what's going on before you even start answering the questions. But you got a vertical circle. It's moving clockwise. They even label this here, and they label this in subsequent parts as well. It's moving through a circle, and we know that if it's moving in a circle, it requires a centripetal force. But unlike a horizontal circle, the centripetal force in a vertical circle is always derived from more than one force, okay? And that's because gravity, the acceleration due to gravity, which acts only in the vertical, is always applied to the ball moving in that path. Okay, so it says, on the figures below, draw and label all the forces exerted on the ball when it is at points P and Q respectively. Now remember, they told us when it's at P, the string is horizontal, and when it's at Q, it's at the top and the bottom, meaning the string is going to be vertical. Okay, so when we have a ball on a string, we know that there are two forces always involved, and as the ball goes around the string, there's going to be a tension pulling inward on that ball at all times. Now there's also going to be a gravitational force, which we might label mg, that's always going to be pulling on it at all times as it's going around the circle. Now they only want us to label it point P and point Q, so let's go ahead and take a look at what happens here. So first of all, the easiest one to remember is that gravity, or the acceleration due to gravity, the weight force, always points downward toward the center of the Earth. And because this is a vertical problem, or a vertical circle, we can label this one mg and label this one mg. Now they do show you with a capital M, so I really should probably use a capital M to show this as well. Okay, but that would be the force on the object due to the acceleration due to gravity. Because it's on the end of a string, there's also a tension force that points inward towards the circle, and a tension force that always points inward toward the circle. Now, how do we know it's always pointing inward toward the circle? Because it's someone holding this string in the middle, and so it's got to be pulling towards where the person is holding it, or where it's being fixed somewhere in the center. Now, they're silent in terms of how to draw these vectors in terms of the length, because of course the magnitude of the tension is going to change as it goes around the circle. It's going to be smaller here, for example, at P than it is at Q, because of course it's also supporting the weight. But they're silent on that, so it's probably not a huge issue if you make these the same length. And we'll take a look at the scoring guidelines from the College Board in just a second to show that. This was worth 4 points, so you want to make sure you take care in drawing all the vectors that are involved. Now they're only talking about forces. They're not talking about velocity or acceleration as they might have in other questions. So you only want to talk about the forces that are acting on it. Couple of things. One, this is a centripetal force that causes this object to stay on the circle. Okay, a ball on the in the circular path. In this case, the centripetal force is made up of both T and mg. So it would be incorrect to draw the centripetal force Fc, so to speak. It is typically something that you don't want to put on your free body diagram because it is often a mistake. It is often erroneous in terms of what the force is, except for a very limited number of situations. For example, in this situation at point P, the gravitational force acts perpendicular to the tension, and it acts tangent to the circle, so it cannot provide any centripetal force whatsoever. It cannot contribute to any centripetal force whatsoever. So technically, in this particular diagram at point P, you could, or actually if there was another point over here, wherever it's horizontal, you could label this force, this red force here that's horizontal towards the center, you could label that Fc. But it's just much easier to avoid using Fc in your free body diagrams because that's the only place that it's Fc, or as I said, if there was a second point over here, you could label it Fc. It is never the centripetal force anywhere else on the circle. Anywhere else on the circle, it's always a combination of these two forces, the mass times gravity, which is the weight force, and the tension towards the center of the circle. So those are our four forces labeled correctly and diagrammed correctly. And we'll look at the scoring guidelines, as I mentioned, in just a minute. Okay, the next question says, is derive an expression for the minimum speed that the ball can have at point Z at the top without leaving the circular path. Now, the minimum speed is going to happen when that ball just gets up to the top and just gets through the circle without having the tension pull on it. In other words, the minimum speed, if it leaves the circular path, that means the tension is no longer pulling on that circle. Now, they didn't ask you for a free body diagram, but you could sketch one really easily, and if it's point Z up here at the top, you know that you have the tension pulling inward, and the tension is going to be least up here, by the way, and then you have mg force, which never changes, okay? And as we slow this down, so this is the minimum speed we're looking for, as we slow this down, what force is going to change? Well, we know the weight force can't change because it's a function of the gravitational attraction of the ball and the earth. The tension force, however, does change. As we go slower, it requires less tension to keep it on its circular path. And at some point, that tension will sink to zero, in which time the only force that's holding this ball on its circular path is the weight force, the mg force. Okay? So, again, anytime we're talking about forces, anytime we're talking about deriving things and looking at multiple forces acting on an object, the most important thing you guys can do is start with a second law statement. So the sum of all forces, or the net force, equals mass times acceleration. Now, of course, because we're moving in a circle, the sum of the forces is equal to mv squared over r, which is just the centripetal force. Okay, now all forces that act on this ball in terms of its circular motion equal the centripetal force mv squared over r. Now, the first thing we want to say is that there are what the forces are acting. Okay, what forces are acting on this object? Well, a lot of people say, well, what's the formula for net force? Well, there is no formula for net force. That's why we draw a free body diagram. Okay, free body diagrams are important not just to explain your understanding for the problem like we did in part A up here, but also sometimes to help you derive the expression and the answers for your equation. Okay, so what are the forces? Well, we've got mg and we've got t. Well, t points toward the center, so that's going to be a positive force, and by convention, anything towards the center is positive, anything away from the center is negative. Because mg also points toward the center, and I'll do a big M this time again, it's also positive. And there are no other forces acting on this ball at this time. They don't talk about wind resistance. They don't talk about the mass of the string. It's negligible, so it doesn't make any difference. So all of those that is the net force. So that is the net force. That's that side of the equation. All of this equals mv squared over r. Okay, so now we're ready to think about what this minimum speed. Now again, remember, as we slow this speed down, as we slow this ball down, the force that changes is the tension. And once the tension goes to zero, it's only the weight force that keeps this ball on its circular path, pulling it towards the center of the circle. Anything less than the critical speed, this minimum speed, the weight force will pull it down away from its circular path, and it won't remain on its circular path as they describe. So what does that mean? That means at the minimum speed, let me just put a different color here, at the minimum speed, that means that t equals 0, okay? And so when t equals 0, I'm just going to rewrite this whole thing again just to be clear. So t plus, mg equals mv squared over r. We know that when the gets to the critical speed, we know t equals 0 as we set up here. Therefore, mg equals mv squared over r, and I think you see where we're going here. The m's cancel on both sides, and we end up with an expression that says g equals v squared over r, which is interesting in and of itself, because what this says is acceleration towards the center, which is required for centripetal force, is always v squared over r. And in this case, at the critical speed, the minimum speed, it is the acceleration due to gravity that is creating that force. Okay, so once we see that those m's cancel, and we're solving for the minimum speed, don't forget to answer the question. We know that means, and I'll change colors just one more time, just so we can make sure we're okay. And we know that then the minimum speed is just going to be the square root of gr. Now, again, this is an expression that comes up all the time. Whether it's the minimum speed around a circle, the minimum speed around a loop-de-loop, the minimum speed over the maximum speed over the hill when the car loses contact. But don't just write this down. You may know this, and you may have this memorized. You may have read this question and said, "Oh, minimum speed in a circle it's root gr." Okay. Don't just write it down. They want to see this thought process, this reasoning strategy. Again, in terms of the given quantities and fundamental constants only, don't plug in 9.8 for g. Okay, just don't do it. Not only is it not necessary, but they don't want you to. That's why this point is the part that I highlighted up here. Okay, next part. Now we've got a different question. Now notice this says the maximum tension. They want to know the maximum tension in the string that can have without breaking is T max. Okay, so they're telling you that the maximum, that's the strength of the string. It says derive an expression for not the minimum speed, but the maximum speed the ball can have at point Q without breaking the string. Now, here we go. Let's say, why at point Q? Well, because as we go faster and faster and faster, we know the tension is going to increase. How do we know that? Because as we increase the speed, we know the weight force can't change, so the tension force is going to have to increase to help us with that faster speed. We know that the tension force is maximum here because it's not only supporting all the centripetal, it's supporting the center directed force, but it's also supporting the weight. So we want to know what the maximum speed is that it can have at point Q. Again, does it ask us for a free body diagram? No, but let's go ahead and draw one, and incidentally it's the same one that's up here. When the ball's down at point Q, we have a tension T in the string, we have mg down, and now we can start again with a free body diagram and a second law statement. Always, 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 F equals ma. Because this is a centripetal force, we know that the centripetal force, net force towards the center, is mv squared over r. And now we can actually say that we can again do our free body diagram and look at our forces, and now we have a slightly different point. So at point Z, so this is at point Z, I should have maybe said this is at point, I'm sorry, this is not point Z, this is point Q, pardon me. I should have said maybe this is at point Z up here. Okay, but at point Q, notice we have tension again, positive towards the center, but now we have mg away from the center, so it's going to be negative. Okay, and that of course again equals, let's follow our color scheme here, mv squared over r. Okay, now when we look at this here, they're asking us for the maximum speed. They're not asking us for the tension. They're not asking for the rate. We know all of these things. They've given us the tension as the tension max. And so we're looking for the critical speed that this happens. Now, notice a lot of people want to say, oh, the m's always cancel. And that's why it's dangerous to always memorize these things. Because in this case, the m's don't cancel. Because we know we're going to have a value for t, and there's no m in this term, so the m's can't cancel out of this. So how are we going to do this? Well, the easiest way to do this is simply just solve for v. Okay, so again, I'm going to write this expression again up here, all in one color, so we can keep track of what's going on. mg equals mv squared over r, and when we solve, we're going to multiply both sides times r, we're going to divide both sides by m, and then we're going to take the square root, so we're going to end up with v equals the square root of, what are we going to have? We're going to have r over m times t minus mg. And that's the answer. That's as simplified as we need to get. Okay. Now, if you ended up combining the terms over here with the m's, notice there are two m's in this expression. They're the same m, but they're appear in two places. You might have come up with something different. A common alternative answer might have been something that looks like this, where it's v equals the square root of r times the quantity t over m minus g. Now, those are both algebraically equivalent, mathematically equivalent if you plugged in the numbers, but either one of those is correct. Okay, you just want to have an expression that accurately represents the maximum speed. Okay, and I think that's it for that part. So either one of these is fine, and you just want to make sure you box your answer or circle your answer so they know what you're looking for. Okay, if you're confident that that's the end of the point. Okay, the last thing that it says, suppose the string breaks at the instant that the ball is at point P. Okay, so again, it doesn't ask me to draw a diagram, but I'm going to, just because it's going to help me. If you remember, this was point P up here, and as it's going around, remember, it's going clockwise. Okay, and so as this ball is going around clockwise, they're saying the string breaks here. What would happen to the ball? Well, you have to think about what the motion of the ball is at that point. Well, the motion of the ball at that point is straight up, tangent to the circle. In fact, the speed of the ball at any given time is tangent to the circle. So when the ball is, if the ball is released here, it has an initial velocity of a straight up vertical velocity. How do we know that? Because they told us when it's at point P, the string is horizontal. So the first thing that I'm going to say is that it will travel straight upward. Ball continues tangent. You could write that. Straight up, I think, is probably important to write. Straight up. Maybe you want to say vertical. You know, any one of those. Okay, so it continues straight up, vertical, tangent to the circle. Now, describe the motion. It doesn't say describe the speed. It doesn't say describe what happens. It says describe the motion. Well, what's happening to this ball? Once the string is broken, that's just like a ball. You know, someone taking, standing here and, throwing a ball upward. Okay, if they throw the ball upward with an initial velocity, what's it doing? Well, it starts with initial velocity, but what happens? It starts to slow down immediately because the ball will accelerate at negative g. Now that's how I wrote it. You could say the ball will slow down. The ball will slow down due to gravity. Gravity will pull the ball down. Anything like that. Okay? Now, a link to this document will be on the description, but let's go ahead and take a look at the scoring guidelines for this from the College Board. Okay, let's see how we did. So the first one was to draw the vectors, and I want to point a couple things out here. Notice they say, sure enough, we have the mg down and the t pointing inward and the t pointing upward and the mg down. Notice the lengths are the same for the t, so they were silent on that. But it's important to understand how they score these. It says for each correctly drawn and appropriately labeled force, you got 1 point for a total of 4 points. It says 1 point was deducted, and this is a classic AP scoring rubric. 1 point was deducted for each incorrect force to a maximum number of points earned for the correct force. In other words, the lowest score awarded would be 0. And then this is that business about the centripetal force. You can't call it the centripetal force, but no points were deducted if you called this FC over here. Okay. For the second part, the part with the minimum speed, meaning when the tension goes to 0, they got you 4 points for that. So the first, they wanted you to actually show the second law, so some net force equals some physical force, correctly identifying that the mg force, the weight force, is the only force, meaning that tension equals 0, and that's what we said here, tension equals 0. Then it says for substituting the expression, so setting them equal to each other, and finding the correct answer was your fourth point, which is the root RG. Now they use the capital R and the capital M. It's probably a good idea to try to do those things and use those same letters when you complete your questions, but they probably won't take any points off if you use the lowercase r like I did here. Okay, the last part that's sort of algebraic was finding the maximum tension that it can have. The maximum speed for the maximum tension. Same thing, net force equal to some physical force, indicating that the force is the difference between tension and gravity, so that's what we have here. That's what the net force is. For substituting the expression equal to centripetal acceleration or centripetal force, that's what we did here. And then finally doing the algebra. Now notice they have the algebra with the m's in 2 places. It's not going to matter. It will be either one of these, the blue or the green here. Okay, and then of course the last one, what happens if it breaks at point P? Well, the ball is going to go straight up, but just like the ball player problems, we know the ball goes straight up, but it's going to accelerate at -g as it's coming down. So it's just going to say slowing down. They didn't even actually ask you to say gravity. Okay, so again, the link will be in the description for these documents. Hopefully you did okay. Just as a matter of side note, this video is running at about 22 minutes. This problem would probably only be allotted about 10 to 15 minutes on the test, but with all the explanation that we've given, it's taken a little bit longer. So good luck. If you have any questions, please let me know in class. Thanks.